Welcome viewers. Today's lesson is the sphere. This lesson is aimed at our second year undergraduate students in the subject of mathematics. This concept of the sphere is a very famous concept in the three-dimensional coordinate geometry. First, let us start with some real life examples of the sphere. A ball is a sphere. A soap bubble is a sphere. A soap bubble is a sphere. A drop of water is a sphere. A drop of water is a sphere. Our mother planet, the earth, is almost a sphere. In this lesson, we discuss the analytical equations of a sphere in the three-dimensional coordinate geometry, and we also discuss necessary and sufficient conditions for a second degree equation in the three-dimensional coordinates x, y, z to be a sphere, and later we also discuss the plane sections of spheres. Now, let us consider a fixed point O having ordered coordinates ABCs. So, O is the ordered triple ABC, and let us consider a non-negative constant R. Here R is a constant, it is positive or 0, and a sphere is locus of points whose distances from this fixed point is the constant R. I am repeating, a sphere is the locus of points P whose distances from the fixed point O is the constant R. Means, if the point P is at the distance of R from the point O, then that point P is on this sphere, and conversely every point on this sphere is at a distance of R units from this fixed point O. So, we can define the sphere precisely mathematically as follows. Definition: the sphere is the locus of points whose distances or distances from a fixed point O having coordinates ABC are equal to the constant R. The sphere is the locus of points whose distances from a fixed point O having constant coordinates ABCs are equal to the constant length R, which is non-negative. Well, let us take the point P as a general point on the sphere. Let its coordinates be x, y, and z. P is a point in the three-dimensional coordinate geometry, so it will have three coordinates, x, y, z coordinates. Let them be x, y, z. Now, we are assuming that this point P is a point on the sphere. Therefore, by definition its distance from this fixed point O is the constant length R. So, distance OP is equal to small r, and if we square this on both sides, we have OP square is equal to small r square. We know the coordinates of P, we know the coordinates of O, so we can write down what is OP square. That OP is the Euclidean distance between the points O and P. Therefore, OP square becomes x minus a whole square plus y minus b whole square plus z minus c whole square, right, is equal to r square. Y is the point the order triple ABC, and P is the point the order triple XYZ. We know the Euclidean distance between these 2 points OP is nothing but is the length of the line segment OP, that is square root of x minus a whole square plus y minus b whole square plus z minus c whole square. Take the difference of corresponding coordinates, take their squares and add them. And if we take the square root of this, it becomes OP, because we have OP square. Here that square root will not be there, and that is equal to r square. Here x, y, z are the coordinates of the point P, and this point P is any point on the sphere. We say it is a general point of the sphere, and here the constants a, b, c and r are fixed. Here a, b, c are the coordinates of this fixed point O, therefore they are some numbers, and r is again a constant length. Therefore a, b, c and r are constants, x, y, z are variables. These are the variables in the three coordinates. Therefore this describes the equation of a sphere, and this in fact is called the analytical equation of sphere. We can expand these squares. When we expand these squares, we get the following equation: x minus a whole square becomes x square minus 2ax plus a square, and y minus b whole square becomes y square minus 2bx plus b square. It is like a minus b whole square. Z minus c whole square becomes z square minus 2cz then plus c square is equal to small r square. X minus a whole square is x square plus a square plus minus 2ax. Similarly, y minus b whole square is y square plus b square minus 2by plus z minus c whole square is z square plus c square minus 2cz is equal to right hand side is r square. This is the expanded form of this equation. If we look at this equation, we can make the following observations. Number 1 is, this is a second degree equation in the variables x, y, z. The highest power of x or y or z is 2. So this is the second degree equation, and this is a second degree equation in the variables x, y and z in 3 coordinates. And the first point to note is the following: the coefficient of x square and y square and z square are all equal. Those are equal to the unity 1, and we do not have the terms x y. The term x y is not present, the term y z is also not present in this equation, the term z x is also not present. These are missing. These are not part of this equation, and there are first degree terms, and this is the constant term a square plus b square plus c square minus r square is the constant term. Now let us come to a general equation of a sphere. Let us generalize the equation of this sphere. Before going to the generalization, let us look at some numerical examples. Let us take O as the point 1, 2 and 3, and radius r as 4 units, and let us form the equation of the sphere having O as center and r as radius. Well, first let us define what we mean by center and what we mean by radius. Previously we were discussing O as the constant point a, b, c, and here this constant point or fixed point is called the center of the sphere, and the constant distance r is called the radius of that sphere. The fixed distance r is called the radius of this sphere having center as O. Now let us write down the equation of the sphere having O as the fixed point 1, 2, 3 and radius as 4 units. So here in this equation we have to take ABC as O. So O is equal to 1, 2, 3 is equal to the ordered triple ABC, and R is 4 units. Here O is the ordered triple 1, 2, 3, it is the fixed point, the ordered triple ABC. two ordered triples are equal, therefore, we have to equate the corresponding coordinates. A is equal to 1, B is equal to 2, C is equal to 3. Now, let us substitute these in this equation. So, it is x minus 1 whole square plus y minus 2 whole square plus z minus 3 whole square is equal to r square. R is 4, it is 4 square. So, in this equation, x minus a whole square plus y minus b whole square plus z minus c whole square equal to r square, we are writing a, b, c as 1, 2, 3 respectively. A is 1, B is 2, C is 3, and R is 4 units. So, right hand side becomes 4 square. Now, this is the equation of the sphere having center as the order triple 1, 2, 3 and radius as 4 units. And conversely, if we are given a second degree equation representing a sphere, for that sphere we can find out the center and radius. Let us look at an example. Let us consider the equation x square plus y square plus z square plus 8x plus 10y plus 12z minus 4 equal to 0. Let us generalize the equation of a sphere. Here for minus 2a let us take 2u, for minus 2b let us take 2v, and for minus 2c let us take 2w, and for the constant a square plus b square plus c square minus r square let us take d. Then we have this form x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus d is equal to 0. This equation can be put in this general form. We have x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus d is equal to 0. This is a first degree equation, this is a second degree equation in the variables x, y, z. Coefficient of x square, y square, z square are 1s. We do not have x y term, we do not have y z term, we do not have z x term, and these terms are present. And if this represents, if this has to represent a circle, then it has to satisfy the following conditions. If you compare this with this equation and try to find out the radius becomes the following. In fact, here we form perfect squares, that is x minus a whole square terms. This is x square term, this is 2ux term, this contributes for x plus u whole square. Similarly, y square term plus 2vy term, these contribute for y plus 2v whole square, y plus v whole square, y plus v whole square. Then z square plus 2wz contribute for z plus w whole square is equal to r square. If we assume that these are equal to r square, then we can show that r square is equal to u square plus v square plus w square minus d, because x square x plus u whole square is x square plus 2ux, means here we have added u square. Similarly, y plus v whole square means y square plus 2vy, means we have added v square here on the left hand side. Z plus w whole square is equal to z square plus 2wz and plus w square also, means the term u square plus v square plus w square is added on the left hand side. So, we have to add it on the right hand side also. Then we get r square is equal to u square plus v square plus w square, and this d also is to be added on both sides. So, that gives r square is equal to u square plus v square plus w square minus d. So, whenever we are given this kind of an equation, then this equation represents a sphere having center as minus u minus v minus w. It becomes minus u minus v minus w, and radius becomes square root of this. and this expression being r square, this has to be greater than or equal to 0. So, whenever this equation is considered, if the constants u, v, w and d satisfy this condition, that is u square plus v square plus w square minus d is greater than or equal to 0, then this equation does represent a sphere, and in fact the center of that sphere becomes minus u minus v minus w, and the radius of that sphere becomes u square plus v square plus w square minus d under root, because this is radius square. Well, here these minuses are very important. We compare this equation with x minus a whole square plus y minus b whole square plus z minus c whole square is equal to r square. So, in place of minus a we have plus u, and here the center is having coordinates ABCs. So, if ABC are coordinates, here the terms minus a minus b minus c are present. That is why if plus u plus v plus w are present, the center has the coordinates as minus u minus v minus w, means here the multiple of x, the multiple of x is 2u, take half of it, and for that you take minus. Similarly, the multiplier of y is 2v, take half of it, that is v, and take negative sign for that, and multiplier of z is 2w, half of it is w multiplied by minus, and this contributes for the center of the sphere, and radius can be calculated using this expression. Now, let us come back to this question. We are saying this is the let us consider this equation, right, and check whether this equation represents a sphere or not, means we have to test this condition. Here 2ux, let us compare these two equations, right, x square plus y square plus z square tallies with this, 2ux is 8x, therefore 2u is equal to 8, means u is 4. Similarly, 2vy is 10y, therefore v is 2v is 10, 2v is 10 means v is 5, and 2w z is 12z means w is 6, w is 6, and plus d is minus 4, d is minus 4, and if this test is if this condition is true, then this can represent a sphere. Now, let us consider this expression, u square plus v square plus w square minus d is equal to u square is 4 square plus v square is 5 square plus w square is 6 square minus d. D is minus 4. So, minus becomes plus 4. U square plus v square plus w square, these are squares of these three terms, those are 4 square, 5 square, 6 square, add them and take negative of d, that is minus of d, d is minus 4, minus d is minus of minus 4 is plus 4, add all these, and these are all positive constants, therefore, this is a positive term. Therefore, this expression is positive, therefore, it represents the square of a positive real number, and the square root of this becomes radius, and that is why this equation does represent a sphere, and the radius of this sphere becomes the square root of this term, square root of this constant, and center becomes, we have to take for u v w the negatives, that is center becomes minus 4, minus 5 and minus 6. For u v w we have to take the negatives. So, minus 4, minus 5, minus 6 becomes the center of this sphere, and radius becomes square root of this expression, that is 16 plus 25 plus 36 plus 4. For that we have to take square root. When we simplify this, we get 16 plus 25 plus 36 plus 4. So, this is 40, 56, 61, 81. So, radius becomes square root of 81, this is r square term is this, therefore, radius becomes square root of this, that is root 81, that is 9 units. So, for this sphere, center is this one and radius is 9 units. So, that is how we can determine whether a given second degree equation represents a sphere or not in 3-dimensional space. If in case this expression is not correct, if in case this inequality is not obeyed by these by the constants present, by the constants u v w d present in this equation, then that equation is not certainly a sphere. If in case it obeys this inequality, it does represent a sphere, and for that sphere we can find the center and the radius as we have done here. Now, let us look at another general form of this second degree equation. Let us look at another example of a sphere. Let us consider the equation x minus a whole square plus y minus b whole square plus z minus c whole square is equal to r square. Let us consider the sphere having the origin as the center and radius as r units. Means the center O is ABC is equal to the origin. The coordinates of the origin are 0, 0, 0, means A is 0, B is 0, C is 0. Therefore, this equation becomes x minus 0 whole square is x square plus y minus 0 whole square is y square plus z minus c whole square, z minus 0 whole square is z square is equal to r square. So, this is the equation of the sphere having center at the origin and radius as r units. Means to look at one numerical example, if we consider x square plus y square plus z square is equal to 3, this is of this form where r is root 3 because 3 is root 3 whole square, and for root 3 if we take a positive value, this is a sphere having center at the origin and radius as square root of 3, which is approximately 1.732. Now, let us look at 4 points and see how to find an equation passing through them. Let us consider 4 points. Let us say these are non-coplanar. Let us consider the points, the origin and 0, 1, minus 1, minus 1, 2, 0 and 1, 2, 3. Whenever we are given 4 non-coplanar points, we can show that those 4 non-coplanar points determine a sphere. By non-coplanar we mean all these 4 points do not lie in the same plane. Now, let us see how to find a sphere passing through 4 given points. To determine such a sphere, let us consider this equation x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus d is equal to 0. Let us say this is the equation of a sphere passing through these 4 given points. What we do is we substitute each of these points in this equation. So, when we substitute the point 0, 0, 0 in this equation, x becomes 0, y becomes 0, z becomes 0, and correspondingly we get a condition on the coefficients u, v, w, d as follows. So, 2u into 0 is 0, this becomes 0 because y is 0, z is 0, therefore, this also vanishes. So, we get d equal to 0. So, this we are assuming that this sphere is passing through this point, therefore, constant term vanishes. Similarly, this we assume that this sphere also passes through this point. So, substitute x equal to 0, y equal to 1, z equal to minus 1 in this equation. So, correspondingly we get 1 square, that is 1, plus minus 1 whole square, that is 1, plus 2u into 0 is 0, plus 2v into 1 is 2v, plus 2w into minus 1 is minus 2w, plus d is 0. So, it is 0. So, when we substitute 0, 1, minus 1 for x, y, z respectively in this equation, we get this condition on u, v, w. Similarly, when we substitute these two, we get, when we substitute x equal to minus 1, y equal to 2, z equal to 0, we get 1 plus 4, then minus 2u, then plus 4v is equal to 0. Similarly, when we substitute x equal to 1, y equal to 2, z equal to 3, we get 1 plus 4 plus 9 plus 2u plus 4v plus 6w is equal to 0. So, here these 3 are 3 equations in the unknowns u, v, w. U, v, w. In the unknowns u, v, w, these 3 equations are obtained, and from these 3 equations we can determine the values of u, v, w, once we know u v w, because we have already got d, we have got all the 4 unknowns u v w d. Therefore, we have got the equation of the sphere. So, solving these 4 equations, we can obtain the values of u v w and d. We will substitute them back in this equation, and that gives the equation of the sphere passing through these 3 given points. So, whenever we are given 4 points, we can find an equation of a sphere passing through them like this. Here the non-coplanarity plays an important role. If these 4 points are not non-coplanar, then there will be a unique such a sphere. In this lesson, we have started with the concept of a sphere. We looked at certain examples of spheres. We showed a ball is a sphere. We discussed the analytical equation of a sphere in the 3-dimensional coordinate geometry. We derived conditions for a second degree equation to be a sphere. We also looked at some numerical examples of spheres, and finally, given 4 non-coplanar points, we learned how to find a sphere passing through the given 4 non-coplanar points.